Okay, so here's where we are, the week of April 24th, starting a new topic on eigenvectors and eigenvalues. That's what spectral theory is. We'll get everything that you need. There are eigenvectors and eigenvalues on demonstration 3, but we'll get everything we need done this today. And on Thursday will be some application, beginning of some applications, and probably these applications will spread into next week. But none of the applications are on the demonstration, although some of them are on the, in a very simple way, on the exercises on Rig X that are on, that correspond to this topic. And this weekend, we have demonstration 3, the last demonstration. And also up now is the last assignment, assignment 7. Now you can see it's a zip file because it has 2 items in it instead of just the LIX file. It has the LIX file and if you when you download it, it's a zip file, so you extract it and you get a folder, and it has in it the LIX file and a picture, a photo, a diagram of a. Let's look and see what that is. So when you open the LIX file, you should see this image here. Now, if you don't, you may need to click on this and then browse and find this image in case your operating system has some problems. Also, now what you're going to do in this particular problem is you're going to find the determinant. We write down the determinant that calculates the area enclosed by the 2 vectors here in the dotted line, and then you're going to sort of take this image, perhaps from the file in the folder, and annotate it. If you don't change the name, just annotate it and save it back with the same name. It should just appear here. And again, if it doesn't appear here, now the problem is you have to keep you want to keep the folder with the LIX file and the diagram in the same folder so that you can know where everything is. But at the end, when you turn it in, when you choose export and export as PDF, then the image will be included in the PDF file, and you'll just need to turn that in. It will be good just in case, like to make sure that when you actually turn it in, that you post it on Piazza and then download it and look at it to make sure that your diagram hasn't somehow been left out. Okay, that's the last assignment, and I will get up a second version of assignment 6, but it's not up right now. And there's about this assignment 7 has 2 topics: determinants and finding eigenvectors and eigenvalues. And the Rig X exercises that are just on this topic are finding eigenvectors and eigenvalues. So that's the task, and that's what's on the demonstration. And so we'll start talking about that if there are no questions so far. Okay, so the first question is, what are eigenvalues and eigenvectors? First off, the word eigen, of course, is a German word that means self or characteristic, something like that. But it has a nice sound in English. You can sort of eigenvalue sounds sort of like it's got some heft to it, so to speak. Okay, so here's the situation. It only applies. This topic only applies to square matrices. So it's like and determinants will appear, and because all the matrices are square, that's okay. Now the other Okay, well, let's go ahead straight to the definition is, here's a situation. You have a square matrix M, and it turns out that for some vectors, V, you multiply the matrix times V, and you get back a number times the same vector back, right? So this is the situation. When this occurs, this is, well, we use the Greek letter lambda for the eigenvalue. It's a number. Oftentimes, formally it has to be a complex number because you can get a complex eigenvalue, but the ones we'll see will all be real numbers. And the ones like usually when you measure stuff or when they apply in applications, you end up with matrices that have real eigenvalues. So we'll always have real eigenvalues. Now, so if this is true, and you get the eigenvalue lambda here, then V is the eigenvector associated with lambda. So each eigenvalue, sort of eigenvalues and eigenvectors come in pairs. A matrix, this square matrix is going to have multiple, can have multiple eigenvectors and eigenvalues. And so that's the definition. This is the definition of what you mean. Okay. Now the crucial thing, one crucial thing is that row operations change eigenvalues. So we can't, this equation only makes sense for a given matrix. If you do a row operation, it's a different matrix that will have different eigenvectors and eigenvalues. So it's characteristic of the matrix, so that it's like before a linear system, the linear systems will appear later in finding eigenvectors and eigenvalues, but in the definition of an eigenvector and eigenvalue, these lambda and the vector V here are associated with the matrix M. You know, this, and that's why they're called characteristics. They're somehow characteristic of the eigenvector and eigenvalue, a characteristic of, of M, the matrix M. And if you do row operate, so we can't do row operations to like find lambda and the eigenvector V. Okay, so the question is then, how do we find the eigenvectors and eigenvalues? Okay. Yeah, here's sort of there's a procedure, and at the beginning there's a little sort of derivation. So let's look at this equation and see what some consequences are. Well, first I'm going to subtract lambda times V from both sides. So I'll end up with MV minus lambda V equals a zero matrix, right? Because of the zero vector, because this is a vector here, so we're going to put an arrow over it because it's a zero vector. Now you notice that's okay. That's just subtracting the same vector from both sides. You get one vector minus the same vector zero, and it appears on the other side. But the problem is that I'd like to factor out the V, but I can't because this is a matrix and this is a number. So what I do is I notice that V equals the identity matrix times V. Okay, so that introduces a matrix here, and then lambda V equals lambda times I times V. So I'm going to use this sort of fact to introduce the identity matrix here so I can factor out V. So you have M times V minus lambda identity matrix V equals 0. Okay, now I've got a matrix here, a matrix here. I can just use the properties of matrix multiplication because that's formally matrix times a vector, which is a special kind of matrix, matrix times a vector. So write this as M minus lambda I, the identity matrix, times V equals the 0 vector. And one important sort of change that's relevant right here, so it's worth mentioning, is V is never the 0 vector. In other words, you notice that a 0 vector satisfies this no matter what lambda is, right? If I put in the 0 vector here, M times a 0 vector is 0 times a 0 vector. So that's a trivial case that we rule out. Eigenvectors can never be 0, okay? So here, V is not equal to the 0 vector, right? Now what this equation says is, this M minus lambda I is a given square matrix, right? And the crucial thing is that, let's say that, so this matrix here, let's just look at this. Let's say that some matrix times V equals a 0 vector. So this is, we're going to establish something about this. Well, if this is true, let's say that B was invertible, right? So if B is invertible, it has an inverse, meaning, so I can write B inverse B equals B inverse times the 0 vector. Well, this matrix times the 0 vector is just going to equal the 0 vector, right? And the B times the B is going to give the identity matrix times V, and that's going to give me V equals 0. So if you have this situation here in which you had a matrix times V equals 0, if this matrix is invertible, then the 0 vector, if this is true, then this has to be true that V is 0. But we're looking for the situation, we want eigenvectors which are not equal to 0. Therefore, this cannot equal 0. The only way that can occur is for B here to not be invertible. Well, this is just a standard for this, for M minus lambda I to not be invertible. It must be a singular matrix, right? Therefore, its determinant is 0. The determinant of M minus lambda I equals 0. So that the only way that we could have this situation, so the idea here is to have this work with V not 0, it must be the case that the determinant of the matrix minus the eigenvalue times the identity is the number 0. Because it's singular, okay?
It has to equal 0 because it's not invertible.
Yes,
okay.
Because if it's a matrix that has, if the determinant is 0, think about what that means for a square matrix. What it means is that if I brought that matrix to row echelon form, then it would have diagonal entries, along the long diagonal. And if all of those entries were not 0, it would be invertible because there'd be no free variables, right? And also, so as a result, one of those values has to be 0 because there has to be a free variable. Okay, but if there's a free variable, that means that one of those diagonal entries is 0, so the determinant is 0. So that means that the only way you can have a non-invertible matrix is if you have a free variable which corresponds to the determinant. So there's a chain of consequences there from the last chapter that we sort of didn't highlight maybe as extensively as we should, but there it is. Okay, so now it turns out that because this is a square matrix, when I take the determinant, it's just going to become a polynomial in lambda. Determinant m minus lambda I equals 0. This is a polynomial in lambda. This will become clear when we actually do a special case. So this polynomial is called the characteristic polynomial. Okay? This equation is called the characteristic equation. It's just the characteristic polynomial equals 0. So what we have to do is, but the point is this: if let's say that we find a lambda for which this is true, then it's going to turn out that we're going to have for every solution here, we're going to end up being able to solve the system for the eigenvector v, and we'll have an eigenvector and eigenvector. So the eigenvector and eigenvector. So this whole derivation is something that you have to understand why it's true, but you can just start here and say, okay, because this is true, step 1, this has to be true. And the procedure is to find lambda is going to involve solving this polynomial, the characteristic equation, the characteristic polynomial, the characteristic equation, solving it for lambda. And it's going to turn out that because if over the complex numbers, we can always factor this if the matrix is n by n, it's going to be an nth order polynomial, because at most there's going to be lambda to the n in it. And that means there's going to be, if we take up the complex numbers, there's going to be n roots, and we can all factor it into a form like this of lambda minus number, lambda 1 times number 1, lambda 2 minus number 2, say, dot, lambda n minus number n equals 0, because it's a polynomial, and of the complex numbers, there's a theorem that says I can always factor that polynomial into things. Now, these numbers here might be complex or real. So, but then you can see that this will be true whenever lambda I equals the corresponding number. So that means there's the eigenvalue. Okay, so let's stop here and see how this works in practice. Let's do an example. Let's let M equal the matrix, say 1, 1, 1, 1, like that. Okay, so what we want to do is we want to look at m minus lambda times the identity, which equals 1, 1, 1, 1 minus lambda 1, 0, 0, 1. There's our matrix that we want to have the determinant being 0, right? So we form this matrix. Now, since this is lambda is only multiplying the identity, this becomes 1 minus lambda, 1, 1, 1 minus lambda. So our characteristic polynomial is the determinant of 1 minus lambda 1, 1, 1 minus lambda. Now, you notice since we have a lambda in here, using Gauss's method to sort of find the determinant is a little bit awkward. So we want to use the formula that if you remember from last time, that the determinant of A, B, C, D equals AD minus BC, AD minus BC. That's like this is a special case of the formula. We'll have to use the 3x3 one also. So then what this so we can see here what this is this will be 1 minus lambda squared. That's lambda 1 minus lambda 1 minus 1 times 1 is 1, right? So if we multiply this out, that's going to be 1 times 1 is 1. We have to do this. Let me write it. Let me write this without the square, just to sort of make the multiplication easier. 1 minus lambda, 1 minus lambda, minus 1 times 1. So this one's 1 times 1 is 1, minus the n terms, minus lambda times minus lambda is plus lambda squared. Then I have in the middle the cross terms, minus lambda times 1 and minus lambda times 1. Well, that's minus 2 lambda minus 1. So there's the characteristic polynomial. In fact, the ones here cancel. So I have lambda squared minus 2 lambda. So the characteristic equation is lambda squared minus 2 lambda equals 0, because we set this determinant to 0. And now we can factor the polynomial. Because it can just be factored straightforwardly into lambda times lambda minus 2 equals 0. So you can see the eigenvalues are 0 and 2. Now we're always going to choose names for them where just to be convenient for the assignments and stuff, we're going to choose the lambda, we're going to choose, say, lambda 1 to equal 0 and lambda 2 to equal 2. So we'll always choose lambda 1 is less than lambda 2 if we had 3 of them. I'll do this is just for convenience of so we'll all agree which one is lambda 1 and which one is lambda 2. Okay, so this is, we found the eigenvalues. And this is the procedure to find eigenvalues. You come up here, get the matrix. You can see you can start right away from this matrix here, right? You can just form this one right away by just subtracting lambda from the diagonal entries. So all the other stuff is like, there's all this sort of universal, this derivation to get here. So you're always going to be able to just sort of write down the formula for the characteristic polynomial and then multiply it out if it's a small matrix like a 2 by 2 or 3 by 3 matrix. Okay, well there's the eigenvalues. That's half the battle. The next half is the next part is finding eigenvectors. Okay, well, we go back to the original equation and say, well, m times v1 equals lambda 1 times v1, and m times v2 equals lambda 2 times v2. Okay? Well, we can actually play the same trick that we did before by writing this equation as lambda 1 identity v1, subtracting this from both sides to get m minus lambda 1I times v equals the 0 vector. Now we know there's a solution because this has no inverse, right? But this is a linear system. We actually have two linear systems, right? Over here we'll have m minus lambda 2. This is V1, V2 equals 0. So we have to go and solve both of them, right? And you notice that we know what this one is. For our matrix here, this is 0 here, and this is 2 here. So we can just write down, we can just construct the linear system here like this as 1 minus lambda 1, 1, 1, 1 minus lambda 1 times x, y equals 0, 0. There's my linear system, right? Written as a matrix equation. With the particular, so I've just taken the original equation. So it's just this form here. Once I have this form, right, I can just proceed here and say, I have a linear system, right? Well, that's the same. We have, that means here's the augmented matrix for this system. Is just going to be 1 minus lambda 1, 1, 1, 1 minus lambda 1. Well, it's not a determinant. 0, 0. And I'm going to put in, so, but I'm putting in here the particular values for lambda 1. So for lambda 1, I use the fact that lambda 1 equals 0. So there's my linear system. There's no excess lambda because it's the particular values I found when I factored the polynomial equation. Well, we can obviously do minus row 1 plus row 2 to bring it to echelon form. And you can see then that this is just the equation. If I translate this back to equation, this is just x plus y equals 0. So as a result, the leading variable x has to equal minus y. So therefore, so every solution, so every vector xy up here with x equals minus y. So every vector with minus y is an eigenvector. So it's really an eigenspace, right? It's like because y can be any real number. So what we're going to do is we're going to choose a representative eigenvector, which is sort of we're choosing a basis for this one-dimensional eigenspace. Okay, so we're going to choose y. How are we going to choose y? Well, what I want to do is I want to choose y. Let's have this is a social convention. Choose by convention. Choose y so that this leading variable up here is positive and has no fractional part, right? So here I can choose y equals minus the smallest number. So you want y to be the smallest positive number that has no fraction. Y makes top component smallest integer, smallest positive integer with no fraction. This is just a convenience. So, because then our representative eigenvector is 1 minus 1. So this is V1. We're going to say V1 equals this. So we'd report that is M has eigenvalue lambda 1 equals 0 with eigenvector V1 equals 1 minus 1. And of course, any multiple of this is also an eigenvector. It doesn't, it's like it's not just, it's like you can see here, because this is homogeneous, I could multiply this whole equation by a number, and that's going to change a non's. I can just check. There's nothing. There's no significance to the absolute value here. Sometimes you want to change this so it's you might want to choose y so that v is normalized, right? So it has magnitude 1. But then we get all kinds of messy components in here. And that makes grading problems difficult. So we want to keep things as simple as possible. So that's our convention. Okay, we found, so, and you can just, you can say, if you were an assignment, you just say, now we have lambda 1 equals 0 with v1 equals 1 minus 1, okay? But then we have to do the same thing with the other one, right? Because the other one was lambda 2 equals 2. So therefore, 2, we can just proceed right away with 1 minus 2, 1, 1, 1 minus 2 times x, y equals 0, 0. But now this is V2. Well, that has the augmented matrix, minus 1, 1, 1, minus 1, 0, 0. Okay. And again, we do the row operation of row 1 plus row 2 to get minus 1, 1, 0, 0, 0, 0 to echelon form. And then we see that minus x plus y equals 0 is the condition for a solution. And that means that x equals minus y, whereas, no, x equals y. Good. Otherwise, we'd be in trouble. Eigenvectors different eigenvectors have to have different eigenvalues. So x equals y is the condition. Therefore, V2 equals y, which we choose as V2 equals y equals 1, 1, 1. So therefore, lambda 2 equals 2 has eigenvector V2 equals 1, 1. Okay, and there you have a matrix, you found through a long process the eigenvalues and eigenvectors. Let me